Hello everyone, this is Dr. Aeronautics, and today we're finally diving into an exciting topic. Shuttle-style atmospheric entry and descent into a giant planet, the ultimate abyss. We'll be covering a few topics in this video, namely how a giant planet comes into being, what the planet is physically like, atmospheric entry basics and the challenges presented by giant planets, the plan of attack for a successful giant plan entry, a note about my atmospheric mod, and then a step-by-step spaceplane flight from low Neptunian orbit through entry, drop out into free atmospheric flight, and the long descent from the clear skies high above through layers and layers of clouds to the darker than night interior region of the planet. I have this video separated into chapters so that you can skip around for your convenience, and just a note that the spaceplane flight will be in a separate part 2 video to be released at the same time as part 1. A note about all of this is that I'm not a professional astronomer, but I am an amateur astronomer, and I do read many papers on this topic, especially atmospheric retrievals of super Jupiters and brown dwarfs. So we're now going to cover how a giant planet comes into being. So at the very beginning, you start with a protoplanetary disk from a collapsed nebula. That's pebbles containing stones and metals, frosts of water, ammonia, methane, hydrosulfide, and more, as well as copious amounts of hydrogen gas forming around and in the star. Eventually, gravity will cause these pebbles to clump up like snowballs and create rubble piles that are a few hundred meters or 1,000 feet across. And these are called planetesimals. In fact, the asteroid Bennu is a great modern day example of what this would have looked like. Once the rubble pile reaches about 1 kilometer in size, or half a mile, the planetesimal's gravity is now strong enough to begin to attract material through its surroundings instead of only plowing through its path like a snowball and accreting. We think this results in a rapid growth to around 350 to 400 kilometers across, about the size of Mimas or Ceres, where there is now enough gravity to cause high pressure on the center, which compresses the insides to evenly distribute the weight around. And now the object is roughly spherical and called a protoplanet. We currently understand through NASA science that Ceres is actually a unfinished protoplanet. The protoplanet can continue to grow until it runs out of silicate rocks and metals in its vicinity. This usually happens when the object is 1 to 2,000 kilometers or 1,000 miles in diameter. This is why we have so many objects of that size in the solar system. At this point, we'll turn up the heat. Protoplanets now grow by attracting their nearby siblings to each other, growing from collision after collision. There's a huge amount of energy generated in this formation process, and that energy becomes the heat in the forming core of the protoplanet, which can be upwards of 1,500 degrees Celsius or 2,500 degrees Fahrenheit. As the object heats up, it allows heavy metals to sink to the center, while lighter compounds such as silicon crystals and stony minerals rise to the top. The protoplanet is now composed of a metallic core and stony mantle. In the case of the rocky planets, once the outer layer of the mantle solidified and weathered, it became the first crust of these planets. At this size, the gravity is too low and the temperature too high to hold under lighter compounds such as water and hydrogen, so they will outgas and be blown away until the body cools. The protoplanet will continue attracting other protoplanets to itself until it has cleared all protoplanets in the space surrounding it where its gravity can influence bodies in nearby orbits. With this, the protoplanet is now a planet. Now there's some debate on this still, but what happens next probably depends on the state of the central star and the position of the planet. If the star has ignited hydrogen burning, this will drive formation materials out of the system and formation is finished. This is how we think the inner planets of our solar system formed. But if the star has not yet begun fusion of its hydrogen, or the planet is far enough away from the central star, the formation can continue. If the protoplanet was lucky enough to reach around the size of Mars, once the surface cools, any water that falls onto the planet will freeze out into ice if the surface is colder than -100 Celsius. Other volatiles, that's chemicals with low boiling points, may be able to stick. Carbon dioxide will freeze if the surface is below -50 Celsius. Ammonia will freeze if the surface is below -150 Celsius. And if below -200 Celsius, methane can freeze out. If there is sufficiently cool surroundings, lots of water will be available. Other icy minerals, such as ammonia and methane, will fall to the surface. This builds up a thick layer of ice on the planet, which is being warmed by the hot, stony mantle underneath, continuing formation, and if ignited, the central star. An ocean forms, which outgasses nitrogen, methane, and more. This ocean will require either cold surroundings or a large, quickly forming planet in order to survive. Otherwise, the stellar wind will drive these materials away from the forming planets like a defroster. If enough volatiles are available, the ocean will deepen until the entire surface is covered in ocean. Eventually, the ocean will reach a depth where the pressure at the bottom is so high the liquid compresses into an exotic form of heavy ice known as Ice 6. This form of ice is heavier than water and can exist at higher temperatures and can extend downwards hundreds of miles or more. As the object continues to collect icy minerals, the gravity of the object again grows and it starts to attract other forming planets around it. Though the collisions create heat, the gravity of the planet is now so high that it can hold on to the water, ammonia, and methane regardless. In the case of our solar system, we believe all 4 giant planets formed very quickly and pretty much all at once. The planet would have collected enough metals, rocks, water, ammonia, and methane to reach over 5 Earth masses. At this point, a Venus-thickness atmosphere would likely form out of the methane, as it has a low condensation point. This traps the heat of the ocean, which is being convected up from the icy mantle, also convecting heat from the stony, now outer core. Once the top of the ocean's temperature exceeds the boiling point, it will begin to boil down to a depth where the pressure is higher than 22 megapascals, about 220 times the atmosphere of Earth, or 2.5 Venus atmospheres. This is known as the critical pressure, and once the ocean boils to this point, any distinction between the gaseous atmosphere above and the liquid ocean below is erased. The ocean blends into the atmosphere, and this exotic process is what causes the lack of surfaces in our giant planets. If the planet grows beyond 5 to 10 Earth masses, finally, the helium and hydrogen gas will be captured. The planet rapidly takes in all surrounding gas in space until there is none left, either because it has been blown away by the star initializing fusion or consumed in other planets. From 5 to 10 Earth masses, there is very little growth in size of the planet while mass grows. The exact reason for this is unknown, but it is probably because the hydrogen and helium are being forced into the oceans as a solvent rather than blanketing thicker as an atmosphere. But after 10 Earth masses, as hydrogen continues accumulating to the saturation point of the oceans, excess hydrogen will continue to build up the atmosphere and the planet sizes will grow again. Because hydrogen and helium are lighter than everything, only a few hundred parts per million of anything else will be able to stay aloft, and these gases will dominate the upper atmosphere. And because these are the most abundant elements in the universe, they are available in enormous quantities. Despite being light gases, there can be hundreds of Earth masses of it around. In the solar system, formation of Neptune stopped with about 1 Earth mass of hydrogen. For Uranus, 1 to 2 Earth masses. For Saturn, around 80 Earth masses. And for Jupiter, around 275 Earth masses. As the thick hydrogen atmosphere, which can accumulate to between 100,000 and 1 million times the mass of the atmosphere of Earth, loads an enormous pressure comparable to 300 to 2,000 kilometers or 200 to 1,250 miles of rock on Earth. It causes the deeper hydrogen to take on exotic properties, the ocean to further freeze into strange forms of ice or boil into plasma, deeper ices to turn ionic and possibly into plasma phases, and rock iron cores to heat to temperatures higher than the surface of the sun. Since Neptune and Uranus are 17 and 14 Earth masses respectively, and their atmospheres only 1 to 2 Earth masses compared to water and ammonia content around 10 Earth masses, they are called ice giants to distinguish them from the gas giants, which are truly mostly gas. If we take a look at Jupiter and Saturn, with 312 and 93 Earth masses respectively, their hydrogen and helium atmospheres comprise 250 Earth masses for Jupiter and 60 for Saturn. The gas giants feature even more exotic forms of matter, such as metallic hydrogen, which is a phase where hydrogen starts to act like a conducting metal. I should note that we do know now that if you take a look at Jupiter, it's split into 2 possibilities. We know that Jupiter exhibits the possibility on the right side, which is a diluted core, and thanks to the Juno mission from NASA. We can see here that we believe Jupiter formed very, very quickly and sort of all at once. The core, which was the rocky part of the planet, reached about 15 Earth masses in just 500,000 years. At that point, it began the gas accretion phase, which is where the volatile minerals such as ammonia and water and methane started to condense to the surface. And when it reached about 50 Earth masses, then runaway hydrogen gas collection took over, and the planet very quickly grew in size until it ran out of material and formation was finished. Interestingly, once a planet has reached about twice the mass of Jupiter, it stops growing in physical size around 150,000 kilometers or 90,000 miles and reaches a compression threshold. This is because the added pressure further compresses the core to denser matter states, and the planet can be called a super Jupiter. If it keeps collecting more mass, the size will actually shrink. At 13 Jupiter masses, it will be able to fuse deuterium, a rare form of hydrogen with 1 neutron in the atoms, and the planet will glow red like a stove. And we call these brown dwarfs. Still shrinking in size, around 65 Jupiter masses, lithium is able to be fused and a photosphere of surface plasma is formed. And finally, around 80 Jupiter masses, the core is compressed enough for hydrogen fusion to start, and a star is born, and the star quickly grows in size, again with added mass. Amazingly, though the entire brown dwarf accretion process, the object continues to shrink in size with increasing mass, with the heaviest brown dwarf and the stellar fusion threshold being the size of Saturn, but over 250 times denser. This is over 10 times the density of the metal osmium the heaviest natural substance that can be accessed by human technology. We're now going to talk about what giant planets are physically like if you were to visit them. The safe upper atmosphere of the planet would be a pilot's dream. Endless skies and levels of towering clouds like floating mountains with no bottom. Like the Earth, all 4 giant planets have an exosphere, thermosphere, stratosphere, and troposphere, but no mesosphere. The atmosphere is surprisingly similar to Earth's. There's gases, clouds, rain and snow, but no ground. Instead, cloud deck after cloud deck is reached, each one with less daylight than the one above it. The apparent surface we see from space are blankets of clouds at various depths, also referred to as the cloud tops. Exactly the same appearance that you would see in an airliner flying above a cloudy region underneath of you. On Jupiter, the white clouds areas called zones are clouds at 70% of one Earth's atmospheres of pressure. The red belts are probably clouds at 2.2 times Earth's atmosphere's worth of pressure. When speaking in terms of pressure, astronomers often use units of bars. 1 bar is equivalent to 1 Earth atmosphere of pressure. That's 101,325 pascals of pressure, or about 14.7 psi. 10 bar is 10 Earth's atmospheres of pressure, 1 bar is 1 Earth's atmosphere of pressure, etc. Believe it or not, the Earth actually exhibits a similar visual 2-deck system. From space, we can see the white water clouds, which are generally between 0.5 and 0.7 bar, and the ground or ocean surface at 1 bar. On Saturn, the cloud tops are uniformly around 1 to 2 bar. And on Uranus and Neptune, the cloud tops are also 2-tiered. Thin white clouds sometimes form around 1 bar called bergs, which cast shadows onto a deeper global cloud deck at 5 to 7 bars, which forms the blue-green canvas that we see. Remember that many types of ices, such as water, ammonia, and methane, are present and taken up during the formation of the planet. On Earth, only water is abundant, which means only water forms in clouds. But in all 4 giant planets, lots of methane and ammonia is present too, meaning that if conditions are right, those chemicals will also form clouds. Clouds tend to form at altitudes where the air temperature intersects the condensation temperature for a particular liquid, generally around its freezing point. For Earth, the freezing point is normally found between 0.5 and 0.7 bar, also referred to as 500 to 700 millibar, that's thousandths of a bar, corresponding to 6,000 to 18,000 feet. The temperature changes in height in an atmosphere due to thermal gas laws. In order for an atmosphere to be in equilibrium, that is, energy balance, the temperature must also decrease as pressure decreases due to altitude by an exponent according to the gas's ratio of specific heats. That's called the CP over CV, or gamma. For Earth, and curiously the giant planets as well, gamma is about 1.4. For Earth, the average surface temperature is 15 Celsius or 60 degrees Fahrenheit, and from there, as you ascend, the air cools according to the equation on the screen. That's why it is so cold at altitude. If it were actually equal to the ground temperature, energy would actually be transferred to the system as the air fell. Where the Earth warms from the sun, it introduces energy into the atmosphere. The air gets hotter than it should be adiabatically, and the heat rises to reestablish the equilibrium. Clouds will form at the condensation level and build into thunderstorms if the heat is high enough. This adiabatic temperature law is also present on the giant planets, which means, like the Earth, As you go deeper into the atmosphere, the temperature increases. Water clouds are found on all four giant planets, and they form at the condensation temperature for water, which is about 5 degrees Celsius or 40 degrees Fahrenheit or more, depending on how much water may be present in the atmosphere. Because of how far these planets are from the sun, the depth that you need to go to reach the water clouds are actually pretty far, sometimes more than 100 times the Earth's atmospheric pressure at sea level. And this might be very confusing because you may have learned in school that the giant planets are very cold. And this is where we need to revisit that out-of-bag temperature rule. When it is said Jupiter is minus 110 Celsius, Saturn minus 160 Celsius, and Uranus and Neptune minus 210 Celsius, that's minus 165 Fahrenheit, minus 255 Fahrenheit, and minus 350 Fahrenheit. The temperature being given is either the cloud top temperature of the highest cloud layer or the height at which the pressure is equal to 1 bar, that is 1 Earth's atmosphere. But remember, the giant planets can form clouds out of different substances, so in no case is the first cloud the water layer. Methane will condense and form clouds around 90 Kelvin. Hydrogen sulfide can form clouds around 185 Kelvin. Ammonium can either condense directly into ammonia clouds at 195 Kelvin or react with hydrogen sulfide to form ammonium hydrosulfide clouds, which can form around 230 Kelvin. Clouds can normally only form where convection can occur. This is limited to the troposphere. The lowest temperature of the troposphere is the top, and this limits what clouds may form. On Jupiter, the 1 bar temperature is 165 Kelvin, but the tropopause, that's the top of the troposphere, the temperature is 128 Kelvin. It only gets warmer from there. This means on Jupiter there cannot be methane clouds. As determined by remote sensing satellites, Jupiter does not appear to have hydrogen sulfide clouds. That chemical is expected to be in the form of hydrogen sulfide. So, in displaying this graph of temperature versus pressure, can you identify what the upper two clouds of Jupiter are made of? That is the yellow bar and the green bar. Ammonia condenses at 195 Kelvin, and ammonium hydrosulfide condenses around 230 Kelvin, if that helps. And they're made of ammonia and ammonium hydrosulfide. The ammonia clouds are the upper white zones, and the ammonium hydrosulfide are the deeper red belts. Water clouds, also expected on Jupiter, cannot normally be seen from space as it is too deep, sort of like the bottom of a lake. But every once in a while, a cloud patch can be seen where the temperature detected is 280 Kelvin. The scientific community thinks we're seeing the water clouds through a hole in the upper decks, which is called a hot spot. This is equivalent to a high pressure zone on Earth, where the skies are crystal clear. So are ammonium hydrosulfide clouds really red? Probably not. We think there's some sort of brown chemical haze hovering over or within the ammonium hydrosulfide clouds, which makes them look red. There's not good agreement yet on what this substance is and why it prefers to only park over the belts. Perhaps it underlies the ammonia clouds. As on Earth, in the low pressure areas, heat can rise and form thunderstorms in the clouds. Water clouds are normally responsible for the vast majority of the lightning on Jupiter because of water's very high enthalpy of vaporization at 2,257 joules per gram. Ammonia's is weaker at 1,371, and methane much lower at 481. If the storms are violent enough, the towering cumulonimbus water clouds can actually poke the ammonia hydrosulfide cloud deck above it and result in a multi-species thunderstorm, possibly creating hailstones of both water and ammonia that fall very far into the planet. Where is this source of heat? It's not the surface because Jupiter has none. It's actually the heat left over from the violent planet formation process. Jupiter is actually still cooling from the day it formed. It would be slightly warmer than Saturn if it weren't. On the giant planets of the solar system, this is the source of heat that drives the thunderstorms. On Saturn, the same three cloud layers are expected. However, because Saturn is colder and has less internal heat to drive thunderstorms to clear the air, the ammonia cloud deck is thicker and obscures everything underneath of it. Uranus and Neptune are colder, which enables them to form methane, hydrogen sulfide, ammonia, ammonium hydrosulfide, and water clouds. Quite an impressive structure. This graphic displays our anticipated water cloud whereabouts for Jupiter on the right and Uranus on the left. As you can see, the highest a Jupiter water cloud could be is about 1 bar, and it's typically around 4 to 5.2 for the base. And humid environments as well as rain can fall as deep as 9 bar. On Uranus, it's a different situation. The cloud layer would likely be anywhere between 10 bar at the top, with the bases between 28 and 43 bars, and possible liquid water clouds extending downwards to 65 bar. Now, below that, we're not exactly sure how much water is present on Uranus and Neptune. That's because we've only had one good mission to it. That's Voyager 2. So we really need more data to figure out how much water is present and how deep a water cloud actually could persist. There are some models out there that say that it could, in theory, persist all the way down to 1,045 Earth atmospheres. So far we've only been talking pressure levels. And remember, pressure changes with height. So at some point we're going to need to figure out height, right? So how do we actually tell those distances and heights? First, we need to assign a zero altitude. Unlike the inner solar system, these planets do not have surfaces, which can be called zero altitude. They're the perfect definition of an abyss. So we're going to have to choose an arbitrary level to represent the surface. The scientific consensus is that the 1 bar level, that is the altitude where the pressure of the atmosphere is 1 Earth atmosphere, is defined as height 0. All locations above it, as you go higher, the pressure decreases. That's positive. And below it, the pressure increases, and that's considered negative altitude. 3 other definitions can be reasonably assigned, and I've seen these in locations. Remember that as you go deeper, the atmosphere warms because of adiabatic rules. At some point, you reach a depth where the temperature is the same as it is on Earth average. This level can also be assigned as 0. A third option is assigning 0 to the cloud tops, whatever cloud happens to be there. This works great for Saturn and okay for Uranus, but for Neptune and Jupiter, which have 2 visible cloud decks, this becomes a little bit tricky. The last one is my favorite. Remember how the tropopause is the coldest location in the planet? It would make a lot of sense to place the 0 altitude where the temperature goes from decreasing in altitude to increasing in altitude. So place the 0 altitude at the tropopause, and above it temperature increases, and below it temperature decreases. Flying in the sunlit portions of the giant planet atmospheres would be difficult. This is because they're 80 to 90% hydrogen and 10% helium. These gases are extremely low density where the air pressure is low. Flying deeper down where the density is higher, this becomes much easier. This is because the density scales with lift per the Bernoulli lift equation. Don't get any ideas about gas balloons or airships either. Since those use hydrogen and helium for lift, and the atmospheres of the giant planets are composed of hydrogen and helium, there will be no lift generated and any airship would sink like a rock. This is similar to filling an airship with normal air and expecting it to fly on Earth. It would simply be a building. The only ability for balloons to fly would be either hot air balloons or solar balloons. Lift would be about 6 times lower than it would be on Earth. And this is actually something that has been proposed by NASA in several studies. For airplanes, for a given pressure level, the density is about 4 times lower on Uranus and Neptune and 6 times lower on Jupiter and Saturn, meaning 4 to 6 times less lift. Again, the deeper you go, the easier it becomes. Worse yet for Jupiter, its gravity is 2.5 times higher than on Earth. Remember the density compression? Meaning 2.5 times more lift is needed at all times to counteract Jupiter's heavy weight. Worse still for Jupiter, its gravity is 2.5 times higher than on Earth. Remember the density compression? Meaning 2.5 times more lift is needed at all times to counteract Jupiter's heavy weight. Saturn, Uranus, and Neptune's gravities are comparable enough to Earth's gravity that adjusting airspeed would be sufficient to generate the necessary amount of lift. Remember, there's no oxygen in the atmosphere, but with plenty of available hydrogen there, if liquid oxygen is carried as fuel on board, it can be reacted in an engine to produce thrust and water vapor. As you descend, the air gets denser, flying becomes easy, though with crushing pressure, high temperatures, and crushing darkness, there is a definite limit to how deep you can fly. So here's a question. How hot can the atmosphere get? Well, since the atmosphere blends slowly with the ocean mantle, which itself is an exotic phase, and the atmosphere is the mass of Earth or larger, it perfectly insulates the interior mantle of water, ammonia, and methane, trapping the formation heat of the planet. Thus, the bottom of the atmosphere is the temperature of the outer regions inside the planet. In the case of Uranus and Neptune, that's about 2,000 Celsius or 3,600 degrees Fahrenheit. For Jupiter and Saturn, it's over 7,000 degrees Celsius or 12,000 degrees Fahrenheit. Yes, that's right. I always laugh about how people say that the most harsh environment in the solar system is Venus. It isn't. It's the bottom of the giant planet atmospheres. 15 million psi, over 10,000 Venus atmospheres, and hot enough to boil tungsten, the substance with the highest known boiling point. Good luck even designing a cube of it to reach that point. If you still don't believe me, ask Google about what happened to the Galileo atmospheric probe. Wait, a probe? That's right. Though sadly we don't have any pictures taken, the Galileo spacecraft contained a probe that entered Jupiter's atmosphere in December 1995. It collected data for 58 minutes before Jupiter's atmosphere destroyed it, likely due to the circuits in one of the avionics boxes overheating. It was about 350 degrees Fahrenheit, and the air 3 times as dense and 22 times the pressure as Earth's atmosphere when it failed, so the fact it survived this far is a testament to how well it was built. What the probe did collect was instrumental in determining how much energy was being released by Jupiter, which is quite surprising. The other item of note was that it included a flux meter, which actually measured the thermal inputs as well, but it also measured the ambient light. The light from the sun is 25 times weaker on Jupiter, which is still bright on human scales since our eyes perceive light exponentially. On the right side of the screen where you see A and D, that is measuring the thermal flux from Jupiter. That is the heat coming up from within. And on the left side of the chart, B and E, is measuring the amount of solar incident light that was available from the sun. Now, Jupiter actually rotated so quickly that the sunset actually happened while the probe was still measuring light during its descent. But luckily, a science team was able to normalize the data and account for this and create a model which provided daytime equivalent values, which is what's up on the screen now. The flux meter model basically indicated that no light was received below the 14 bar line, meaning everything below 14 bar would be dark, and any deeper than that would be as dark as a cave. Now, it should be noted that the Galileo probe entered a clear hotspot in Jupiter's atmosphere, so this is the exceptionally clear condition. We also have scientific papers written with data from telescopes and the Voyager spacecraft on Uranus and Neptune. Those also suggest 14 bar is the depth at which no sunlight will reach, as 7 bar is the deepest that light returns to space. That would be 7 bar down and 7 bar back up to be able to see it on board the spacecraft. For a total of 14 bars pressure traversed, which is great consistency. Now, it may not be 100% to 14 bar. It depends on how many clouds are below the 7 bar layer. If it's all clouds from 7 bar to 14 bar, it would probably be darker a lot sooner. On the other hand, if that part of the atmosphere were clear, then there might be some more light stretching further down. At this point, we now have everything we need to construct a picture of what would happen to a spacecraft entering an ice giant planet like Uranus and Neptune. I'm not going to dwell on the upper regions much here, because part 2 of the video will cover that. The spacecraft coming in at orbital velocity would begin to encounter atmospheric drag in the lower thermosphere. As it reaches the stratosphere, heat and plasma will build and cause the heat shield to rise to several thousand degrees. The cold atmospheres have little power to keep things cool because of how thin they are. Once the entry is finished, the spacecraft will be just above the tropopause. Temperature will be about 55 Kelvin at 1/10 of an Earth's atmosphere. The sky would be a deep navy blue as a bit of relay scattering would work its way in. The spacecraft enters the troposphere and temperature increases. At around 60 Kelvin or 0.2 of Earth's atmosphere, the first tenuous layer of methane aerosol will be encountered, causing the sky above it to turn a more cerulean. Below, it would be a flat sea of greenish teal hydrogen sulfide clouds. Around 80 Kelvin or 1 bar, the spacecraft passes under altitude 0, effectively becoming inside the planet. A bright white methane cloud berg may be passed. Another layer of haze is encountered, which is thicker on Uranus than it is on Neptune, and this is believed to be what causes the slight color difference between the two planets. At the 4 bar level, the spacecraft will enter the hydrogen sulfide cloud deck, which forms the image of the planets as seen from space. The sun will be taken from view at this point. Somewhere below the 7 bar level, the spacecraft busts out of the hydrogen sulfide cloud layer in a dim twilight, now having miles of clouds above it. There's a gap until about 20 bars where the ammonia clouds lie. Because of the fading light, these clouds would appear as a dark shroud below us if this region is relatively clear. Once the ammonium cloud deck is reached, it becomes as dark as night. And when the cloud deck is exited around 40 bar, the surrounding abyss may be briefly illuminated by the flashes of lightning from water clouds below. At 50 bars and a temperature of around 200 Kelvin, the spacecraft enters the water cloud deck. The spacecraft may be buffeted around, and thunderstorms and bright flashes can be seen as lightning strikes. At this point, the pressure is as high as it is 500 meters under the surface of the ocean. So the vehicle is now better referred to as a submarine, and is now keeping the pressure out rather than in. Around 85 bars, the water clouds are exited. It is now a comfortable 50 degrees Fahrenheit, but the pressure is now comparable to Venus. Due to the pressure alone, the atmosphere below this point is likely to be murky to whatever light source there is. The lightning from the water clouds above would fade into the darkness. Any pressure hole at this point would now have 1 ton of pressure per square inch on it. The temperature is now rising, just like an oven that had been turned on, and with the increasing density, keeping the craft cool would quickly become impossible. Eventually, the temperature would reach 600 Kelvin or 1,000 degrees Fahrenheit. Here, the pressure surpasses that of the bottom of the Marianas Trench and 10 times that of Venus. Any hope of cooling or pressurizing a vessel would be impossible, and without magic or undiscovered physics, the craft would certainly implode. Below this level, the air itself surrounding the remains of the spacecraft would begin to incandescently glow deep red like fire. The density of the atmosphere is now denser than water. The atmosphere has silently, gradually slipped into an ocean-like fluid. The visibility would likely only be a few meters, similar to water, given its density. Though we discussed clouds already, it is believed that clouds of other elements can be formed in the deeper regions of the giant planets after a large void following the water cloud layer. The next condensation point after water could be cesium chloride, rubidium chloride, or potassium chloride, clouds of minerals. This happens around 1,000 Kelvin. Pressure would be over 5,000 Earth atmospheres. Many other mineral clouds might be encountered on the way down to the ocean. In increasing melting points, lithium fluoride, lithium sulfide, sodium sulfide, and metal clouds of iron, titanium oxide, and aluminum oxide, otherwise known as corundum, which forms rubies. Whatever our spacecraft was made of, it will disintegrate as it drops below the cloud containing that compound. For example, an airplane made of ice would melt away if it dropped below the water clouds, which are above the freezing point of water at the base of the water clouds. Similarly, a craft made of stainless steel will be heavily eaten away as the chromium cloud layer is reached, and evaporate entirely once it drops below the level of the iron cloud layer. We're not sure which of these cloud decks exist and which don't, because it's impossible to see what's going on that far down. This is nearly 1,500 kilometers or 1,000 miles. We can only use magnetic and gravitational detections to infer what might be going on down there, at least when a spacecraft is there. At the titanium oxide clouds, the pressure is over 100,000 bar. The mass of the atmosphere above is equal to the mass of the entirety of planet Earth, which in turn represents about 7% of the mass of Uranus and 6% the mass of Neptune. By now, the incandescent hue of the hot, dense fluids would have passed through orange into yellow and would be turning white hot. The depth is now around 5,000 kilometers or 3,000 miles below the methane cloud tops, and roughly 20% of the depth to the center of the planet. Around 200,000 times Earth's atmospheres of pressure and a temperature of around 2,300 degrees Celsius or 4,100 degrees Fahrenheit. The transition from the hydrogen atmosphere to the water ammonia ocean occurs. This ocean contains about 10 times the mass of planet Earth and possibly features diamond rain and floating diamond bergs, building-sized diamonds that float between the atmosphere and the ocean. It is not known exactly how gradual the transition is or exactly what phase the ocean is in, with evidence to support both an abrupt transition like clear air to fog or a gradual one like haze. But whatever the phase is, it is probably ionic, superionic, or even a plasma phase of ocean. Whatever it is, it has to at least be able to flow to generate the magnetic fields we see around Uranus and Neptune. Likewise, it is not currently known whether the ocean bottom is a slowly solidifying mud of plasma water and exotic silicate phases, or if it is a true bottom like the bottom of Earth's ocean. We need more spacecraft sent to Uranus and Neptune to figure that out. We're now going to discuss atmospheric entry. To enter orbit around any planet in the solar system, it requires an enormous amount of velocity. For the Earth, that is about 7,800 meters per second. The larger the planet, the higher the circular orbit velocity. For Uranus, you need 15,000. For Neptune, you need 16,600. For Saturn, 25,500. And for Jupiter, 42,500 meters per second. This number is important, not because you are launching into space, but because you need to decelerate by this amount to enter free flight, and it's going to be the speed that the apparent wind is going to be meeting your craft. We use the planet's atmosphere to slow us, as there's not nearly enough fuel on board to use rockets. As you likely know, the high velocity results in a huge buildup of gas and plasma. Now, the type of entry that we're going to be using is called the lifting body entry. The vehicle enters the atmosphere in a high stalled angle of attack. This limits the lift and drag vectors to the hull where the heat tiles are, and as a result, that's where our heat loading is. This also results in additional surface area that can be used as drag. Now, 3 properties of giant planets make them particularly hard to impossible to perform the entry when you compare it to a planet like Earth, Venus, or Mars. The first is the initial speeds are incredibly high, meaning the hull heating will be severe to unsurvivable. The heating is a square to the velocity. The atmospheric density is also lower for a given pressure level, meaning the air will still heat us, but not provide significant drag force to slow the high speeds, nor will it provide as much lifting force to counteract gravity when it applies. Which means that, unlike Earth, where you would decelerate at 1 g or 2 g's, on the giant planets, you would descend at a fraction of a g, and only towards the later stages. And for Jupiter, in particular, high gravity will attempt to drag the spacecraft deeper into the atmosphere, which will further raise our temperatures and reduce the amount of lift that we can provide to keep us out of the atmosphere, which will also reduce the surface area of drag because we're closer pointed into the airstream, which means even less reduction in velocity. So all else being equal, the heat will be the square of the velocity. So if an entry on Earth is 8 kilometers per second and 16 on Neptune, a 2000 Celsius entry on Earth would be 4,000 degrees Celsius on Neptune. That is a major problem, as the tiles will melt right off the craft. So to mitigate this, we must fly as shallow as a profile as we can, which will lower peak heating. The lower molecular weight means that the deceleration will be very slow despite the intense heat. This cannot be mitigated because we already need to fly a shallow entry path because of the high speed. Entry will be extraordinarily long, over 3 hours long. Range will be slightly longer than the entire circumference of the planet. But we've already successfully done this once in real life. How did the Galileo probe do it?
The probe dove headfirst into Jupiter with an ablative heat shield reaching 16,000 Celsius and a peak deceleration of 228 Gs. Yes, hundreds of Gs. If you took the ISS orbiting Earth and were to stop it at 228 Gs, it would go from full orbital velocity, that's 17,000 miles per hour or 27,000 kilometers per hour, to dead stop in under 3.5 seconds. Watch my video of the Galileo probe entering Jupiter to see what this looks like. It's over in only a single minute. There's a few problems with this. First, we have tiles, not 80 kilograms of ablatable heat shield. The tiles would melt right off the craft if we tried that.
Second, you probably guessed, but the human body cannot survive 228 Gs. It would weigh as much as 10 tons if it did, the equivalent of having the front of a Greyhound bus on your body, and about 10 times the force of a head-on collision sustained for half a minute. It is for this reason we cannot follow the Galileo probe's profile and instead must use our own.
Is there a limit to our capability? Yes, absolutely. If the ship is cool, we can raise the nose, which causes the lift vector to decrease and drag to increase, causing us to fall faster, as well as exposing more surface area to the airstream, causing us to decelerate faster. If the ship is falling too fast, lift is increased by lowering the nose. This raises the lift vector, opposing the weight vector and slowing our descent. It also means less surface area is exposed to the airstream, making less drag, which increases entry time. The limit is, if the atmosphere is too thin to slow us down while not providing sufficient lift to counteract weight to keep us out of the dangerous condition of high speed and high dynamic pressure, we may be pushed to lower the nose to 14 degrees angle of attack. If we are still falling too fast, it's curtains. At this point, a dangerously high vertical speed means one of two things will destroy the ship. One, we further lower the nose below 14 degrees, allowing the supersonic airstream to instantly reconnect the wings to the airstream, resulting in an explosive increase in lift and wing loading stress that tears the ship apart. Two, nothing is done, and the temperature continues to rise until the tiles are compromised and a burn through happens, allowing 1,000 degree gases into the ship's interior, and the whole thing blows up like Space Shuttle Columbia.
And now our plan of attack. But we must first ask why. We will be flying a very long, difficult, and demanding profile requiring constant attentiveness for 3 hours, razor-thin margins of error, and definitely ends in a guaranteed fatal implosion. And the answer is because it's a fun challenge. And maybe in a million years we'll have something like Cloud City floating in the clouds and this will become relevant. Over the years, I've developed a 7-phase flight plan. Here is the plan for Neptune. The first step is going to be to set ourselves up in the lowest possibly orbit that we can make to minimize the entry velocity. That's the altitude where the atmospheric density is about 3 times 10 to the minus 10 kilograms per cubic meter. For Neptune, that corresponds with an altitude of about 967 kilometers above the 1 bar level. For our simulation, we're actually going to need to add 208 kilometers since orbiter doesn't allow negative altitudes. This gives us a 1175 kilometer altitude plus 24,416 kilometers for Neptune's radius, and that gives us 25,591 kilometers from the center of Neptune for our semi-major axis. The next thing we need to know is the altitude of the atmospheric interface, where active attitude control begins. That should be the altitude where the density reaches about 5.55 times 10 to the minus 7 kilograms per cubic meter. That happens about 415 kilometers above the 1 bar line. And again, we need to add 208 kilometers for the simulation. That gives us 623 kilometers altitude plus 24,416 kilometers. So then we get the final radius of 25,039 kilometers from the center of Neptune, and that represents the interface altitude. We now need to solve an entry or transfer orbit that takes us into Neptune's stratosphere for entry, crossing that imaginary interface line of 25,039 kilometers radius with a flight path angle of negative 0.2 degrees. This is extremely shallow as compared with the Earth, which is typically around 2 degrees. There's two reasons for this. First, we cannot fly an Earth-like entry due to the amount of heat that would be generated in that type of entry. We're limited at just over 2,200 degrees Celsius, or we blow up. Second, we're orbiting the planet at a very high speed, meaning it will take longer to adjust our course to zero vertical speed, which is needed to safely initialize the entry path. Now, I've already generated a solution to the problem, which is up on the screen. We need an eccentricity of 0.01135 starting from our circular orbit. This means the periapsis will be 25,016 kilometers from the center of Neptune, and the entry orbit semi-major axis will be 25,303.5 kilometers. Now, since we're starting from a circular orbit, we can do this maneuver at any time, but we want to consider where we're entering the atmosphere. Our long entry path will take us a full lap around Neptune's circumference. Our entry orbit will take half the planet. Thus, we need 540 degrees of range, and we will likely finally drop in on the opposite side of the planet we do the maneuver on. I'd like to make the final descent into the clouds during midday for maximum visibility. So I'm planning to do the maneuver when we're just before orbital midnight. After the maneuver, we'll drift down and pass through the atmosphere's denser regions of the thermosphere. Since we don't want to alter our flight path yet, we'll fly this segment with the nose pointed in the direction of flight. As we near the interface altitude, the ship's thermal display will begin to report meaningful hull temperatures. They'll start out cold, around negative 200 Celsius. When they rise above 500 Celsius, phase 1 of re-entry begins. In phase 1, we're going to reach the interface, bleed off nearly all vertical speed, and establish a thermally stable condition with low constant vertical speed between 0 and negative 20 meters per second. In phase 2, we'll manage the entry corridor to sustain temperatures to within thermal limits, and a very gentle orbital deceleration begins. In phase 3, orbital speed will have slowed a few kilometers per second, and it now results in a temporary easier deceleration with the thicker air, and that can be allowed to increase our rate of deceleration, and that temporarily happens faster. But then the heating really starts to become a problem. And around 2/3 our orbital speed, so it's around 10 kilometers per second, our orbit decays where gravity is beginning to pull our trajectory down. And that has to be compensated with extra lift by pitching down. But there's a point where we're going to near the critical condition of falling too fast with not enough lift to stop a runaway thermal condition. And this is where our margin of error is at the minimum, and the utmost care will be taken. Our skill levels must be at our highest at this point. Finally, in phase 5, the speed, which will be about half orbital speed, will have decayed to the point where higher dynamic pressures may be accessed, and the craft will begin to slow more due to the lower heating rate due to slower speed. And at phase 6, the cooler stratosphere will be reached, which will enable us to choose an even steeper flight path, and this is where our deceleration will finally start to burn off at half a G. In phase 7, we reach the transition point from our entry to free flight. Just above the tropopause, speed should be below 1 kilometer per second. At that point, we can slowly lower the angle of attack to slow our descent rate and lower our dynamic pressure, then slowly continue lowering the nose to break the stall. Once the stall is broken, we'll establish a glide slope of about negative 5 degrees and a vertical speed of about negative 120 meters per second. Flight will now be gentle. One final thing to note is that the entry takes so long that the APU burn rate as well as the coolant temperature rates must be tweaked in the XRCFG file, as the APU will run dry and the ship will overheat unless those are extended. I don't see either of those being an unobtainium cheat. There are modifications that can either be made to lower the heat generation, such as turning unneeded electrical equipment off. Okay, we're going to briefly talk about my atmospheric mod for Orbiter, because this is not using the vanilla Orbiter mod. So the simulation you're about to watch does not use that vanilla atmosphere that's included on the download with Orbiter 2010 or 2016. The vanilla atmosphere assumes the atmosphere of Neptune is made of air like Earth. It is not. It also assumes that the temperature is 288 Kelvin, that's 20 degrees Celsius, everywhere in the atmosphere. It is not. It also only simulates the atmosphere to 4 bars. So I set out to make a mod to simulate Neptune as it really is. To do this, I made a request on the NASA Technology Transfer Program website to access a model called the Neptune Gram, which stands for Global Reference Atmospheric Model. Neptune Gram is a program that returns mean and statistical atmospheric conditions to provide engineers and mission designers with an engineering-oriented model that can be used to construct hypothetical missions. Basically, in English, it's a Neptune atmospheric simulator. It was initially coded in 2004 and kept up to date as new knowledge is learned about Neptune. I was granted access to download the Neptune Gram and configured it to report conditions from space to the lowermost extent, using the resulting data to construct a C++ module in Orbiter that reproduces the conditions based on the curve fits of the outputs. It is very accurate to Neptune Gram, as you can see. Seeing this, we can be comfortable that the results we obtain in this simulation would match the truth if a space plane were taken to Neptune and entered the atmosphere.